Let's look at some of the exciting examples that can be found in section 2.4, and that may actually help you a little bit with your homework as well. Let's start with number 9. You can see in number 9 that we're given two functions f and g, and we're told they are continuous. So we have that f and g are continuous. Remember what that means. It means the limit as x approaches a for any function, any value a in the domain is going to equal the function evaluated at that point. And we have then that f of 3 is 5, and we have the limit as x approaches 3 of, let's see, the quantity of 2 times f of x minus g of x is equal to 4. And we're asked to find, then, g of 3. Alright, so we're going to use some of the theorems that are found in this section. First of all, we're going to use the fact that the limit of the sum of two functions is the sum of the limits. So, in other words, we can break this up and say this is the limit as x approaches 3 of 2 times f of x minus the limit as x approaches 3 of g of x, and all that is equal to 4. Now, we're also told then that since f and g are continuous, let's see, 2 times, well, we have another limit law that says we can bring this 2 out in front. This is going to be 2 times the limit as x approaches 3 of f of x minus the limit as x approaches 3 of g of x. Alright, and so now what are we going to do? Well, we know that f is continuous. F is continuous, and we're also told that f of 3 is equal to 5. Since f is continuous, that means that the limit as x approaches 3 of f of x, f is continuous at 3, is equal to f of 3. So this is 2 times f of 3, since f is continuous, minus, well, g is also continuous, and so the limit as x approaches 3 of g of x is equal to just g of 3. And that equals 4. We're given f of 3 is 5, so we have 2 times 5 minus g of 3 is equal to 4. 2 times 5 is 10. 10 minus g of 3 is 4. If 10 minus g of 3 is going to be 4, I guess g of 3 is probably going to have to be 6. So using our limit laws and our definition of continuity, we were able to find the value of g of 3. And let's take a look at another example. Let's take a look at number 10, where we're asked to use the definition of continuity and the properties of limits to show that the function is continuous at the given number a. A equals 4. So we need to show that the function is continuous at a, we need to show that the limit as x approaches 4 of f of x is equal to exactly f of 4. Well, that's our definition of continuity at the value 4 for the function f of x. And the properties of limits are going to say that, well, what we have here is a function made up of a polynomial and a root function that's been shifted. But you can see that the domain of f of x, is going to be given by, well, we're going to need to make sure that 7 minus x is greater than or equal to 0, or 7 is greater than or equal to x. X is less than or equal to 7. So that says that 4a, which is 4, is in the domain of f. And since 4 is in the domain of f, we can see then that the limit as x approaches 4 of x squared plus the square root of 7 minus x is just going to be equal to, well, since 4 is in the domain, the function is going to be continuous there, because these are functions where we are continuous at our domain. So we have 4 squared plus the square root of 7 minus 4, which is 16 plus the square root of 3. And that's just equal to the function evaluated at 4. So the important thing to determine here is that we have a function that is continuous because it's a polynomial function and a root function. And if you look at your list of functions that are continuous at every number in their domain, in Theorem 7 on page 122, polynomial function and root functions fall in that category. So really all it came down to was making sure that 4 was in the domain of the function. And since it was, since our domain was x less than or equal to 7, or negative infinity up to and including 7, is our domain for f of x, since the value a, which equals 4, was in that domain, well, then we can see, yeah, it's continuous at that point, and the limit as x approaches 4 does equal just f of 4. Alright, let's keep going while we're hot here. Let's try another one. How about number 16? Number 16, we're supposed to explain why the function is discontinuous at the value of a given. Our function here is a piecewise function, f of x, and it's equal to x squared minus x over x squared minus 1, and that's going to be the case if x is not 1. If x is equal to 1, the value of the function is 1. So you can see that the function, and we're looking, of course, at the point a equals 1. We want to show that f is discontinuous at this value of 1. Well, now the function is defined at 1 because, I mean, if x is equal to 1 right here, the value of the function is 1. So we can see that f of 1 is equal to 1. F is defined there. That's one of the things that has to be true for the function to be continuous. But the other thing that has to be true is that the limit of the function as x approaches 1 has to be equal to the actual value of the function. So if we look at the limit as x approaches 1, well, if we're not at 1, as we're getting closer and closer to 1, we have to use this part of our piecewise function. So the limit as x approaches 1 of f of x is going to be the limit as x approaches 1 of x squared minus x over x squared minus 1. You can see that this portion of our function is not defined at 1, and, well, obviously the function itself is not defined at 1 because this part is only defined x is not equal to 1. But if you tried to plug 1 in here, you would get 0 in your denominator. So we'll have to do a little bit of algebra here. We'll say this is the limit as x approaches 1. Notice in the numerator I can factor an x out. So I get x times a quantity of x minus 1 divided by, let's see, this will factor. This is a difference of two squares, x plus 1 and x minus 1. Hey, and so by the limit laws we talked about in 2.3, the limit of an equivalent function is going to be the same. And so we get the limit as x approaches 1 of x over x plus 1. Well, now this thing is defined. I can plug 1 in. I get 1 over 1 plus 1, or 1 half. But the limit then as x approaches 1 does not equal f of 1, which remember was equal to, f of 1 was equal to 1. So we can see that since the limit as x approaches 1 does not equal f of 1, we can say then that f is discontinuous at a equals 1. A couple more problems here that we want to look at. Let's take a look at number 18. Number 18, we're given the function h of x, and it is equal to the sine of x over x plus 1. We're supposed to state, using theorems 4, 5, 7, and 9, why the function is continuous at every number in its domain, and state the domain. Well, you can see then that we have basically a rational function here, and this rational function is made up of, well, it's not a traditional rational function, and that's a polynomial over a polynomial. It's a function made up of a trig function divided by a polynomial. And sine of x is continuous on its domain. Now, its domain is all real numbers. So its domain is all real numbers. Anything from negative infinity to infinity you can plug into sine and get a value out. And that's by theorem 7. So theorem 7 tells us that. Also by theorem 7, we also know that x plus 1 is a polynomial. Well, theorem 7 doesn't tell us it's a polynomial, but theorem 7 says that since it is a polynomial, it is continuous on its domain, which is all real numbers, which is the domain of x plus 1. So the numerator is continuous on its domain, the denominator is continuous on its domain. Well, that means the entire function, f divided by g, or sine of x divided by x plus 1, is going to be continuous except where it's undefined. So h of x, which is equal to sine of x over x plus 1, is going to be continuous everywhere except where it's undefined, which, as we said, is going to be where the denominator is going to equal 0, except where x plus 1 equals 0, or where x is equal to negative 1. So we are continuous everywhere except at that point at negative 1. And you can see that if you look at the graph here, the function, I just went ahead and plugged it into this WinPlot computer program. Y equals the sine of x divided by x plus 1. You can see that we do have a discontinuity here. It's an infinite discontinuity at x equals negative 1. The function is continuous everywhere. I don't have to pick up my pencil as I draw it, except for when I get to negative 1. I have to pick it up and come back down here. So we have an infinite discontinuity at x equals negative 1. We'll talk more about those in 2.5. And let's look at one more problem then. How about number 26, where we want to use continuity to evaluate the limit. The limit as x approaches pi of the sine of x plus the sine of x. Well, you can see here that the x plus sine of x is inside function. That is continuous at x equals pi. Why is that? Well, because it's a polynomial function plus a trig function. Those are continuous at their domain, and pi is certainly in the domain. The domain of x and the domain of sine of x is all real numbers. And then sine itself is also continuous, all real numbers. So we have a composition of functions that are continuous everywhere. That tells us then that the limit as x approaches pi of the sine of x plus sine of x is just going to be equal simply to the function evaluated at pi. So it's going to be the sine of pi plus the sine of pi. Again, since it's continuous, by definition, the limit as x approaches that number is going to equal the function itself evaluated at that number. So that's the sine of, let's see, pi plus the sine of pi. Sine of pi is 0. And so then we have the sine of pi plus 0, which is the sine of just pi. And again, that is 0. So we get 0 again because that's the value of the function at x equals pi, and the function is continuous at x equals pi. Let's look at that and see an example of that. Let's take this function out, and we wanted the sine of let's see, no, we wanted the sine of x plus the sine of x. And you can see that the function is continuous, and sure enough, the function at 0 is, let's see, the function at pi. Where is pi? That's going to be about right here. Yeah, pi is 3.14, so you can see it about this spot right here, 3.14. The function value is 0. And it's continuous there as we go through, so you just evaluate the function at the point x equals pi. Alright, you should be in good shape for your 2.4 homework. Let me know if you have any questions. The password for the 2.4 homework is obeisance, O-B-E-I-S-A-N-C, and that just means to pay homage to. And I have no idea what that has to do with continuity. Good luck.